Okay, today we're going to talk about, or in this video, talking about ideal solutions. We've talked about ideal gases, but how, if you don't have intermolecular interactions, ideal gases make sense because they're just point particles that are, not interacting with each other. But a solution is by definition liquid phase, which means you have intermolecular interactions and the proximity of the atoms or molecules is actually quite close. Sorry, excuse me. And so the way that we define ideal solution is if you have a solution of A and a solution of B. This A molecule that's just kind of floating in the middle of all these other A molecules, if its intermolecular interaction with all of what we call the nearest neighbors is going to be the same as the nearest neighbor interactions of A interacting with all of these B. So if we took this middle A out, stuck it in the middle of this B solution, and if A couldn't tell the difference at all, that is what we define as an ideal solution. Cool. Okay, so Raoult's law. Raoult's law says, so here's my A, a bunch of A's, and there's going to be a bunch of little A's, the vapor pressure of them floating up at the top. So here's a bunch of A's. So PA star equals the vapor pressure of pure A. Okay, but if I have a couple of B's in the mix, there might be a few B's at the top. And if that's the case, then I have the mole fraction of A times PA star is equal to the vapor pressure, or we're going to call this the partial vapor pressure. Okay, so PA star represents the vapor pressure if it was just the pure system. Okay, so just pure A. But then the partial vapor pressure is now PA star times the mole fraction. So it's out of all of the moles that you have in the vapor phase, how many of them are A, that percentage. That percentage here multiplied by the pure vapor pressure would be your partial vapor pressure. Okay, and likewise, mole fraction B, PB star is equal to PB. We actually used this in the last video. So hooray, you already know this. Oh, and just to remind everybody, this is equal to NA divided by NA plus NB. Mole fraction, total moles of A, or the moles of A divided by the total moles in your system. Okay, so for mixing, we have mu of our component A is equal to mu A star. This is pure plus RT log mole fraction of A. So this is pure A. This is the mixture. So this is A in the mixture. Cool. And then the mole fraction is equal to PA over PA star. Again, mole fraction or vapor pressure of A divided by vapor pressure of the pure. Cool? Okay. So this is then related to the chemical potential of how much work energy you can extract from the mixing of the gases. Sweet. Okay, so now what I'm going to do is I'm going to introduce you to Raoult's law, and I'm going to do that by drawing, or not drawing, but sharing my screen and showing you a Wolfram Demos project of a binary solution. This is a Raoult's diagram. You're going to see vapor pressure of A versus mole fraction of A. And honestly, it's going to be, so mole fraction of A, that means 0 to 1, 0% A, 100% A, or you can say 100% of mole fraction of B, 0. So as A goes up, B goes down. Okay? Okay, so now I'm sharing my screen, and you should see vapor pressures of binary solutions. And here, I've got vapor pressure as a function of mole fraction. This is mole fraction of B. And so I can change the mole. So this is pure B. So this PB0 here, that's the same as our PB star. So that's 100% B. So if I change the vapor pressure of B, I move this way up, watch what happens. There we go. There's a delay. So that says that my vapor pressure of B is much higher than my vapor pressure of A. All right, so if I have two very different vapor pressure liquids and I mix them together, the total along the mole fraction of the mixture, with right here being 50% of the mixture being A and 50% being B in terms of the number of moles present, that tells me that this black line here is how the vapor pressure of the liquid combination, the mixture, would change. And if you think about the height here, this is just a linear addition. So you've got the height of this yellow line plus the height of this blue line. You add those together and you get this. So if you take this height and you add it here, that's where this black line comes in. Okay, so this is Raoult's law. It says that you can add the partial vapor pressures. Just like Dalton's law of partial pressures, you can add the partial pressures of individual gases. Raoult's law says you can add the partial vapor pressures of a solution. But you kind of can't, because now we have chemical identity that have interactions, so it's not quite ideal. If it's a perfectly ideal solution, say you had one of the, here, I'll stop sharing for a second. Okay, so say you had benzene and toluene. I used to do this experiment where you mix benzene and toluene. This is the dumbest idea ever, because why? Actually, no, it's hexanes and toluene. Anyway, this was back in PChem lab when I was teaching it at OU, but whatever. Okay, so if you have benzene, whoops, and then you have toluene, chemically, these are very similar. There's just a methyl group here. And so if you were to take one benzene molecule out and put it into a whole bunch of toluene, the benzene's not really going to see that much of a difference in terms of intermolecular interactions. So it's going to actually think it's kind of the same. Ideal solution. If, however, you mix like acetone and water, huge difference. And so that's when you start to see deviations of how the vapor pressures change. And that gives you some insight into the mixing, the thermodynamics of the mixing. Okay, back to share screen. So now I'm going to show you the deviation from ideality. So if we have a really, I'll just go way up. Boom, isn't that crazy? So the dashed lines show you what the Raoult's law for ideal mixing would be. Let's go even more crazy. Okay, so here you have, as you increase the mole fraction of B, the vapor pressure skyrockets, and then it kind of levels off. Notice how as you get to very close to 100% B, as well as very close to 100% A, you have these rather steep and or linear trends. The main part of the curvature happens more into the mixture. Okay, let's focus on this part first. This deviation is a deviation of ideality for Raoult's law, which is going to be looking at each of them as a solvent. Okay, so I can also go the other extreme. Excuse me. So a negative deviation from ideality. So here, as you mix the two together, so this yellow line plus this blue line equals this now concave total vapor pressure. The total vapor pressure as you mix them together goes down. Lower vapor pressure means boils or doesn't boil. Hopefully you said doesn't boil. So if you mix them together, it's become more stable, higher intermolecular interactions. This designates an attraction of interaction. Whereas a positive deviation from ideality shows that there is upon mixing, especially like right here, that's the highest deviation, you're going to have a higher vapor pressure, which means it's more volatile. So mixing these two things together is actually causing the solution to become more volatile, weaker intermolecular interactions, dominant repulsive forces. All right, last but not least, let's talk about Henry's law. So deviation from ideality. I don't want any deviation from ideality. Let's get back to normal. A little bit less. A little bit less. Close enough. Okay, so we're pretty close back to ideality. Henry's law. Oops, cool. Okay, so Henry's law shows the value of what the solute would be for ideal conditions. So if I do a massive change in ideality, you'll see a drastic change in the Henry's law. And so notice how I was pointing out these kind of sharp curves coming down and then they become linear. So it really, really dilutes. So this is the mole fraction of B. And so this is pure vapor pressure of B would be that value. Here, however, you've got this huge deviation of the vapor pressure. Well, if you take the tangent of that line, empirically now, you can get what's called Henry's constant, which tells you how much deviation you're going to have from pure behavior of the solute as you add it to the solvent. Cool? And if you go even more extreme, it's pretty much the same. Let's go some less extreme. Cool. So as you get more and more ideal, Henry's constant becomes closer to the pure vapor pressure. Awesome. Okay, I'm going to jump to the board and I'm going to show you how that works out. So for those of you interested in brewing, one of the important things that I contribute to the brewery is calculating the Henry's constant for when you add various gas mixtures to the beer. So there's certain nitrogenated beers as well as a certain combination. It's like beer gas is like perfect combination of nitrogen and carbon dioxide to be good for the beer. Anyway, you're now mixing that with a sugar solution. So you've got a sugar solution and you're adding gas to it, which means Henry's constant is actually really important, because you want to know if you're going to be changing the head pressure of the gas, or of the gas is going to be coming out of solution of the carbonated beverage. So, all right. So Henry's law. Oops. Let me grab the other marker. Is P A is equal to mole fraction A times Ka, where this is Henry's constant. And then Raoult's law is PA is equal to mole fraction of A, PA star. Okay. Notice the similarity. PA, this is the vapor pressure of A in the mixture, is equal to the mole fraction of A times something. Mole fraction of A times the vapor pressure of the pure solvent is equal to the partial vapor pressure in the mixture. So Henry's law, and this is for dilute solutions, and I'm going to say ideal. And when I say dilute, I mean you got a solute present. So it might be like an ion or something dissolved and or dissociated in a liquid. So if it's dissociated in a liquid, that means it will be in the aqueous form. So NaCl is a great example. In the presence of water, this becomes Na aqueous plus Cl aqueous. Aqueous means this has what's called a hydration sheath on it, or a solvation shell. Those are common terms in electrolyte chemistry, or you're doing solvent chemistry. I should say solution chemistry, really, to where you have a sodium ion with a bunch of waters. And notice how I have the water spacing. This is OH there, OH. So I have the partial negative facing this direction because this is a cation. So you've got the negative charge of the waters oriented such that they are surrounding this sodium. So aqueous means that this is an ion that has this hydration sheath around it. And if it does that, then you actually have a different type of intermolecular interaction between this hydration sheath or solvation sheath, depending if it's hydration, if it's water as the solvent. If you don't use water as a solvent, if you use some other sort of solvent, it would be a solvation sheath. And in solution chemistry, you actually talk about layers of these sheaths or these shells of solvent molecules. And then you would talk about nearest neighbors, and there's so many neighbors away from the target ion that's either contained within the solution shell. And so the interaction would then be between these water molecules and the farther out water molecules. Okay, so depending on how this interaction propagates through the solution can tell you whether or not your solute is truly dilute enough that it's not affecting the intermolecular interactions of the base solvent. I shouldn't say base solvent, it's not basic stuff, of the primary solvent. Okay, so other thing, dilute ideal solutions. You don't want that intermolecular interaction to change that much. Again, you want it to be ideal so that interactions are very similar. Cool. Okay. Oh, the other thing is this is a limiting law. The amount of solute is very, very small, such that it doesn't dominate. And when I say doesn't dominate, it doesn't change the intermolecular interactions enough that it makes it a non-ideal solution. Cool. Okay. So Henry's law is a way to quantify that, because if you have, so back to the picture, so this is 0 to 1, and this is the vapor pressure. So if you did this, this is PA star. So this is 100% A, and PA star, that's the pure vapor pressure. Henry's constant says it's going to look something, if it's ideal, it will be the same value. If it's not ideal, say, and it looks something like, oops, looks something like this, that's pretty bad. So it'll look something like that. Let's look at what this represents. And this is an extreme case, like I showed you, when it's maximum deviation from ideality. So PA equals 1 times KA. So if the mole fraction is 1, that means that the vapor pressure of the, well, actually, it wouldn't even be of A. It would just be, well, no, it would be, actually. The vapor pressure of this line right here would be way up here, because it's a linear trend. Okay, so this is a limiting law. We're in the limit as the mole fraction goes to 0. Okay, so we're really looking at right there. This doesn't make any sense at 100% mole fraction of A. Whereas over here, PA equals 1 PA star, well, that makes more sense because that is what happens. So Raoult's law really takes effect past at least some amount of A, such that you've actually got the effects of the presence of A in the total vapor pressure. For the mole fraction of the solute, if A is the solute, the small component of the solution, then this is going to give you quite a bit of information. And so it can tell you the extent of deviation of the solute's presence in changing the vapor pressure. Why is that important? If you want the vapor pressure to increase and or decrease, a lot of times you can just add something. And if you add something, now we're getting into colligative properties. This is what y'all are going to do on your own in section 5B, I believe. So the properties of solutions, you're going to look at how colligative properties, or adding, say, salts, solutes to a solvent, are going to affect the vaporization ability, i.e. the chemical potential, to get to an equilibrium between the liquid and the vapor phase. Okay, cool. Oh, other thing, this is completely empirical. We are getting farther and farther away from having a theoretical backing to deriving these things. Someone went into the lab, a guy named Henry, and figured out that this is a linear relationship for very dilute solutions. Okay, this now so you go to a table, you look up your Henry's constant for whatever system that you're using, and that's where you then can move forward to know and anticipate what your vapor pressure will do. Okay, I will post the link for the vapor pressures on the Wolfram demos. Y'all can play with it. Go team.